So as you can see here, the Horizon Technical Community event is organized by the Horizon Cloud. You already know this is an internal event, and although we very much like that you invite any of your peers and collaborators to these kind of events. And today here we have the projects SmartCLIDE and Physics, who are going to present their platforms and talk in detail about the project. So I will just briefly say that who is the next presenter, the next project, and I would request you to kindly introduce yourself in detail. So here we have the first presentation from the project SmartCLIDE, and we have Sebastian here, Theodoros and Zake. Sebastian he is coordinating the project. Please correct me if I am making any mistakes, and I request you to introduce yourself, and the floor is all yours. The next presentation from 3 o'clock will be from the project Physics, and we'll get back to the slide again. Thank you, Sebastian. All yours now.
Thank you, Amrita. Hello, everyone. My name is Sebastian Scholze. I'm working. Let me share my slides. I hope that you can see this now in full screen.
Yes.
Okay, so my name is Sebastian Scholze. I'm working for ATB, Institut für angewandte Systemtechnik Bremen GmbH. And the name already gives a small hint. We are a private institute from Germany, Northern Germany in Bremen. I'm coordinator of this project SmartCLIDE, and together with my colleagues Theodoros and Zaki, we are going to present you the SmartCLIDE project. So the presentation will have 3 parts. I will do the first one, the introduction to the SmartCLIDE vision for a cloud-based IDE. And then we go into much more details, and this will be presented by Theodoros and Zaki. The first one from Theodoros about service creation and composition, and the deep learning engine by Zaki. So what will I show you in my introductory presentation? First, a little bit about our idea and the concept of SmartCLIDE. So includes motivation, approach, which targeted users we have. Then a very brief introduction on our SmartCLIDE pilots. And then, and I think that's the most important, most interesting part, the features of SmartCLIDE. So what is SmartCLIDE? Discovery of services. How can we compose new services? The feature map. And then last but not least, the roadmap. So maybe start with some facts. SmartCLIDE. I have to read the title because it's very long. Smart Cloud Integrated Development Environment supporting the full stack implementation, composition, and deployment of data-centered services and applications in the cloud. So I think that's the typical name of a proposal. And on the next slide, I will guide you what is our idea. SmartCLIDE project started January 2020 and will go until end of this year. Yeah, you can see the contribution, around 5 million euros, funded under Horizon 2020 ICT 2019-2. And on the right side, you can see our consortium, 11 partners distributed all over Europe. I think that's a quite nice mixture, and for further information you can look at our website. Okay, you saw this very long title, but what is this all about? So SmartCLIDE, it's about cloud, it's about learning, it's about an IDE, it's about discovery, and the E for example. What we mean by this? Our aim is to develop a cloud-based IDE to create also cloud applications during this development, we want to learn and give these learned things back to the user. We do not want to do everything from scratch. So we want to discover already existing service to be reused. And we also want, this example stands a little bit for this low-code approach, so that developers can more easily develop cloud-based applications. So what was our motivation, SmartCLIDE motivation? Yeah, digital transformation is changing every sphere of society at a very fast pace. I think that's pretty clear. And it brings technological and cultural breakthroughs. We believe that cloud computing and also agile methodologies on how you develop software, that these are the key enablers of digital transformation. And with SmartCLIDE, the idea is that we can improve this adoption of cloud solutions. What is our approach? I just said, the idea is to boost the adoption of cloud solutions. When we look at current solutions, you find several limitations, and I think we all know them. For example, this what is listed here as first one. If you want to create a solution, a software solution from scratch, that's very time-consuming, complex, and it's very expensive. So, yeah, just that the limitation is that creating new solutions from scratch is very time-consuming, complex, and expensive. And in SmartCLIDE, we are aiming that we can provide tools to have faster and more effective development of cloud services, and also gain deeper insights on how cloud and code works. The second limitation, if you want to create new applications by composing services, this is quite limited because there is no uniform classification and documentation. And it's always a compromise between quality of service and security. What we are aiming at in SmartCLIDE is to provide a more secure and easy way to reuse quality code, and also to gain trust and facilitate the reuse of services. And then the third limitation, what we see is it's very difficult to predict and control the costs of building such applications, and especially if you use the different pricing models of public cloud providers, that's relatively difficult. And our aim is to be a code learning tool, or SmartCLIDE shall be a code learning tool, and that we provide also a deeper understanding of the costs of cloud. What are our targeted users? So in principle, SmartCLIDE could be useful for the whole team. So from Scrum Master to product owner, sponsor, product design. Also for the project, it has a huge value, and also for the end users. But our main focus are the developers, and therefore, yeah, I put here this box around. That's our main focus. It's about it's an IDE, and it's about developing services. Our project is driven by 4 pilots. They are very different. Pilot 1 is platforms for social security organization. That's Intrasoft is providing this use case or this pilot. Then the second pilot is an IoT catalog. That's Unparalleled, an SME from Portugal. The third pilot is from Spain. It's Wellness Tech. It's about real-time communication platforms. And last but not least, the fourth pilot is German SME. They are providing software solutions for PDM, PLM, and ALM platforms. So 4 very different pilots, and they are driving this project, and all of them brought in their requirements and are planning use and try out their development and how this can be improved by applying SmartCLIDE approach. So what is SmartCLIDE? It's a cloud IDE, so smart and cloud native IDE. We believe it's very important that we have a collaboration between the different stakeholders. Then I already said this, we want to compose services, and in order to be able to provide services, we need to provide abstractions for creating control and data operations, and also the possibility to combine these abstractions to create new services. If you want to combine already existing services, of course, you need a service discovery. So the idea is to import, search, and discover available services and resources from current providers. And in order to support this, we are providing a deep learning engine so that we can have an automatic software classification, context identification, and abstraction selections, so that we can support these other two processes, service discovery and service composition. If we go a little bit more into detail about discovery of services, the idea is to automatically expose available resources and cloud services, and this from already existing providers. So from example, infrastructure as a service provider, software as a service. And the idea is to classify them based on their general purpose, but also on the technical requirements. We know that this is not enough, therefore we are aiming to provide additional information to support this composition of new services. For example, it could be description, certifications. Is this service already used by other services or applications? What are the opinions from the end users? And can we compare this with similar services? And we are applying some ontology-based technique to identify cloud service categories. And then for the composition of new services, the idea is that we can create new services from scratch, and also by composing existing ones. And hereby you can see with all these small graphics, we provide high level of abstraction, support full lifecycle, version and configuration management integration, coding by demonstration. We are monitoring the source code to learn from it. We want to have reusable software components that are directly testable, and then also these continuous integration and deployment assistance. When you look at the feature map, on top, we have the SmartCLIDE user interface. It is based on Eclipse-J, and then we are adding there several extensions and plugins so that we can have our functionalities on top of Eclipse-J. And then in the background, we have several backend services in the middle, and you will hear much more details about this is the deep learning engine, but also services for composition, discovery of services, and also the activity monitoring of the developers. And at the bottom, you can see that our aim is not to reinvent the wheel and build another Git, but to use existing tools and integrate them into our SmartCLIDE solution using an API interface. So in SmartCLIDE, we're aiming to support the whole life cycle. So really from planning until deployment, and also after deployment by monitoring the deployed solution. Yeah, and supporting this by packaging, virtualization, and containerization tools. So in fact, it's an extreme automatization of DevOps. Then very shortly, how could this look like? you can see here two pictures, one in the background, that's our SmartCLIDE IDE. And integrated with this, we have this Eclipse.js so that you can develop your software using this well-known IDE. But this is on top then enriched with our services. That's the last slide from my side, our roadmap. So as I said, we started in January 2020. Last year, we had our first prototypes and had some initial testing. And now we are on the road to the final prototypes, which will be available around summertime. Then we have extensive testing by our pilot partners. And by end of the year, we are planning the demonstration. That's all from my side. Theodoros?
Theodoros? Can you? Can you unmute? Yeah, sorry. I sincerely apologize. I don't know how this happened. Let me just, now that we are, exactly how this disturbance happened, but I hope that, we don't have such disturbance anymore. So we had to mute everybody, and so everybody stays mute from now on, and the presenters only when their time will come, then we unmute you. I sincerely apologize, Sebastian. You were interrupted in between, and this was really, really unpleasant. Sorry about it.
No problem at all. It brought me a little bit out of control, but I think we managed it. So Theodoros will present you now some details.
Okay, if I could share my screen, Sebastian.
Yeah, I have to stop it.
Thank you. Hold on a moment, if I could share my entire screen. All right. Good afternoon, I'm Theodoros, and I'll present to you SmartCLIDE service creation and composition component. What do we mean by saying service composition and creation? Probably some of you are familiar with the service-oriented architecture, or in short, SOA. But if not, we will briefly describe the basic idea. SOA applications are ideal for the creation of new, flexible, and scalable cloud-based systems, but are also considered as an ideal alternative to the modernization of old monolithic applications. Through the use of this architecture, large-scale applications are structured as a collection of embedded microservices, which are available on public or private networks. The development process is complex, time-consuming, and demanding, as it is necessary to use many technologies that require specialized knowledge. Here we present a guide diagram with the necessary steps in order to create a SOA application. Let's take a quick look at the steps. Starting off, when creating a SOA application, it is necessary to deconstruct the problem into smaller tasks and to recognize its distinct functionalities. As we're using the SOA approach, each functionality must be associated with a service that implements it. This can be achieved in two ways. Matching can be done with an existing service or with the creation of a new implementation. Let's start by mapping an existing service to one of our functionalities. This requires many steps. The process is very time-consuming and tedious because the user has to search the internet and visit a lot of service registries. The developer must also then read and evaluate every possible service manually. And finally, it must be ensured that the service is functional and accessible. All these steps must be repeated for all of the distinct functionalities found in the problem decomposition step. The other method, as mentioned, is to create a new service. By creating a service, we mean the from scratch code development. For the development, the user needs to interact and use many tools in order to create the necessary structure for software development. The structure may include version control, collaborative development, continuous integration and continuous delivery, and more. After creating the structure, the code writing process can begin, where a framework could be implemented, the quality of the code checked, the implementation tested, and so on. The last step before deploying the software is to perform the service composition. This can be done in a variety of ways, from the creation of orchestration algorithms to the use of special tools and programs. We see that the whole process can be very complicated, as it involves many intermediate steps, especially in the case of implementing a new service. Proceeding to our solution and the way the creation and composition component is structured. SmartCLIDE follows the low-code approach, which is the logic of using as little code as possible in order to create an application. The platform aims to aid in the development of cloud applications and make the process as quick and easy as possible, hiding the complex steps of the process. Finally, we hope to improve the productivity of developers by minimizing distractions and time-consuming interactions with external tools. Continuing with the steps we had previously described, we were able to integrate the steps of problem decomposition and service composition into one tool. This tool is JBPM Workbench. The Workbench implements a widely known standard, BPMN, used for business process modeling through a graphical notation for specifying business processes. Using it, we can create workflows like the one you see, but also more complex ones, where their nodes are mapped to service implementations, such as, for example, a REST service. Constructing a diagram is simple and uses a drag and drop logic in order to add nodes. The diagram can consist of many types of nodes, for example, a script task that executes a simple piece of code, service tasks that execute external services, manual tasks that must be completed by humans, events, etc. Having the deconstruct problem, we can start to add services to satisfy its functionalities. As mentioned before, the next step is to look for the implementations for those distinct functionalities. Now going to the service creation part of our component. This is an important part of the process, as the need for code development is very common. Apart from being very common and important, it is also time-consuming. As we mentioned, the necessary structure needs to be created to support the code development process. And also during that process, it is necessary to monitor the progress of the project and the quality of the code we write. Here we can see the process that the developer is required to perform in order to develop a new service. As of now, we can see the developer starts with creating a repository using Git, and then creating a pipeline for the CI/CD process through Jenkins, for example, configuring Jenkins, going back and forth through Git, the Git client to configure the webhooks, use an IDE to write code, and Docker in order to package it all and make it runnable. Now, having the necessary steps, we can analyze them and automate them as much as possible. We came up with this form of operations to facilitate the development process, where we created 3 services that cover and automate many of the time-consuming and tedious steps of code development. These are the following: the necessary structure creation, the calculation of technical debt, more precisely principal and interest. We'll talk more about this in a little bit. And the calculation of software reusability. Since the central user interface when writing code is the development tool itself, we have integrated these functions into it via extensions. So now let's try and see it in action. Here we have the environment of the JBPM workbench that we mentioned. Let me try and this is hosted on our private server, so it might not be really fast. Okay. In this tool, as I said, we create the workflows and the diagrams. So if we go and to an existing file, let's go to this one. We can start designing workflows. There are many nodes available, as I said, with drag and drop capabilities. Let's create a simple example. Every workflow must have a start and an end node. And let's put a REST service in between. We can connect those nodes simply and creating a business process. Now, what we can do is, what we need to do is map a service to this node in order to satisfy its functionality. We can go here. We can, of course, first change the name of the node. Give it something here, the description of what this node would do. And then we can go and try to assign a service to it. Since we're here, we can see the service discovery also. We can search for an already existing service that takes the description and the name of the node and finds possible matches. And here we have some of them, but let's say that we want to create a new one. Now we're redirected to the IDE that we can write code. This is the Eclipse TIA. And we can start the service creation process. All we need to do is enable the appropriate extensions, provide the necessary fields, which I have noted here. Wait 1 minute. Okay. This all will be automatically filled in and in the background, but for now, we'll do it like this for the demonstration. Let's name it like this. Public. Something like this. We can go to our GitLab user and see that we have these 4 projects. So if we go back and also I didn't mention, we can use Jenkins as a CI/CD engine, but by default we use the GitLab one. So we can run our structure creation component, and we can see that a new project is created. Now, if we go back to our GitLab and refresh, a new project is created, exists there. Right. Here we have our new test demo project open, and we can see several other functionalities. For example, design pattern creation. Let's create something of a rudimentary project source folder inside here, and I don't know if it's cooperating or not, but yeah, here we can choose a singleton pattern, for example, provide have the documentation of the singleton design pattern, write a name, and create the class with those attributes. We can do the same with an abstract factory and so on. Now, assuming we have we've written some code, we need to check for its quality, and we can do that by using another extension that we've created. For example, check Apache's Commons.io principal. We can load an analysis, and we can see the principal of the Commons.io repository as being several hours and some amount of money, and an amount of issues. This is used as a telltale for the quality of the project, as TD principal explains that how many hours are needed in order to bring this specific project into its optimal state by refactoring and so on. So if we go to our interest tab and provide our URL, we can load the interest analysis. Here we can see the files of the projects and the amount of interest each one has, and the percentage of its contribution to the total of the project. The technical debt interest is the amount of extra time required in order to maintain a file, a class, if we compare it to its optimal state. So we can do the same with the reusability, with the maybe I wrote okay. The same for the reusability. We can see the evolution in a graph way. We can zoom in and see it with more details. So, moving on, we can see this is the current state of our component, where we isolated several of the steps required for the developer, and now many of them are automated, many of the repetitive and boring steps. Here we see the before and after comparison of the two procedures. And yeah, we can understand that the developer is spared of the configuration of several tools and the interaction of with several tools, and all is presented inside the central IDE for code development. Thank you.
Zaki, is that your turn now?
Hello, everyone. Yes.
Yeah, okay.
So, hello, everyone. Now I'm sharing. Can you see my screen?
Yes.
Okay, perfect. So here I'm going to give a short overview about the deep learning engine, which is the component in SmartCLIDE IDE that provides some AI-based feature for the developer to help them to provide software easier and correct their error and help them to provide their product faster. So at the first, my colleagues in the last part were mentioned the important concept of SmartCLIDE, but from our perspective, for embedding the AI model in the SmartCLIDE, we need to consider and identify the important concept, and also identify important place that we can provide automation using AI. So the two main concepts are in SmartCLIDE. One of them is service-oriented system development, that we develop that help the developers to use the software that are available as a service. So for the step in service-oriented development is identifying system requirement, finding and discovering the appropriate and proper services for our business to use them. After that, when we find the several services with the same functionality, we need to select the best one. So we in DLE, we are going to provide automation in some tasks that I will show in the next slide. And also, when we want to provide new software and provide software based on our business, maybe we find some available services, and also when we can't find the services, we need the platform to develop it. So when it's come to developing, it goes to the development tools, which main of them is IDE and is well known for a long time. There are a lot of work about this, and as we know, up to now, there are a lot of functionality are in IDE. But in recent year, when we see the well-known IDEs, we can understand that there are two main features that AI had. There are two main aspects that AI help to the IDE. One of them is the improving the current functionality. For example, if the IDE want to suggest the code based on the traditional search algorithms or traditional indexing, now AI comes help with the learning from historical data, give more accurate information to the developer. This can help the developer to increase time of development, and also increase them to provide more accurate code, decrease the human error, and so on. And also, there are some new features in IDEs that these features are new. They aren't just based on the traditional features, and they are something new, like the AI-based code generation, which is a subset of the text generation, which is something new in NLP language, and code generation get things from that. So in this slide, we can see the simple step of service development, and then after I will tell the DLE models and DLE component comes to which of the steps and what help can do with the AI models. So first of all, for imagine we want to provide the software. First of all, we need to discover the services. The services, discovering services, there are some challenges in real world, and things is that discovering services, there isn't unique and universal registry. So developer need to go to the different repository, different places, and disrupt their themselves from their main task. So one of the things that SmartCLIDE have done is the gather the services from the different resources and filter the more popular services, more services that are using in the society and community of developers. And after that, because they are come from different resources, they have different categories. So one of the things that SmartCLIDE do with the AI model was the automatic classifying the services. So when we have services with same functionality and all of them are categorized, it can be easier to find the proper services. After that, service discovery will be more easier for the developer. Then after, as I mentioned before, if the developer can't find the, when the developer finds the proper services, and next they need to compose the services and find the next services to provide their software. So in this stage, DLE comes and help the developer with suggesting the proper services, and this suggestion, most of the suggestions come from the historical data based on the available services, available BPM and workflow, and so on. After that, if the developer haven't found any proper services, they need to develop it and they need to do implementation. So in this stage, DLE in implementation stage comes and help developer with the code generation, AI-based code generation based on huge source of the codes. And after that, for the testing and so on, help the developer. So here, the thing is, all things for the AI and data-driven models is gathering data, always gathering data, good data, the data with the good quality. So when we start designing the codes, designing the models, we understood the main task and main material for us is the text. And this text will be separate to natural language text. For example, we have data about the service description, developer write it, and another is the structural text like code. So based on this, the main task in SmartCLIDE, the main time, not all, but main task goes to AI-based text processing. So as we see, there are I provide the very short summary of the process of text processing in the last years. At the first, there were some keyword-based approach that extract the base and main keywords and then give it to traditional machine learning models and provide some prediction and provide some recommendation. After that, if we in the keyword-based data, when the data increase and we want to work with huge data, then after the dimension of data goes very large. Therefore, the word embedding strategy, static word embedding strategy, comes to the text processing, and okay, word embedding comes, but the better things was coming Globe and Word2Vec and such open source word embedding help developer to provide to embed their text data and provide the better feature engineering for their model. Afterward, in the recent year, the contextual word embedding comes, and the thing is, with contextual word embedding, there are, before we just use the static word embedding for feature engineering. But the good things in here, the BERT and some model like GPT-3 or these things, they have feature, like, they are decoder and encoder, and you can use them as a for feature engineering parts and also for fine-tuning the model. So, when we read the state of the art, we need to notice that as we go to the end, I mean, to the BERT and GPT and transformer, these pre-trained models have a large size. So if we want to put the use transformer for all of the DLE models, we will provide a very heavy backend for us. Therefore, we have two solutions. One of the solutions was for each task we provide the one lightweight model and large size model, and then provide the configuration that the user wants use which of them. But for the task like text generation, which needs more data, huge data, and very good trained model, we use the transformer. So the important things is we needed to work with the open source data and see more data to train our models better. The one of best resources for the service data is programmable build, and also GitHub is the very well now the good resource for the codes that we work with these things, and also for BPMN. We have some internal data set to train our models. Okay, I think we have a time problem. But one of the things that I mentioned was there isn't any universal service registry. And also during the last years, the service are moving from WSDL and SOAP services to RESTful services. Because of this variety of service definition, because of this variation, we needed to have provide some standard for ourselves, and during service discovery, service composition, and during all of these tasks, we provided the service specification. We use the state of the art, and also we use the online resources that you can see a lot of things are for service features in the state of the art, but in the online resources we could find some I think like less than 10 features that we could annotate for all of the services. The models that I mentioned in the previous slides, all of them are embedded in the DLE model. You can see here all of the model are in the backend, and we have served all of this model with the APIs. So if I want to give the very big picture for the models, I will tell about the for our models, data was the important things. We identified the benchmark data set. If the quality of data was good, we use that benchmark data set for our model. But if we couldn't, the model was very overfit, and we need more updated data because some of these benchmark data sets are like for many years ago. So we collected data. After that, pre-process. The pre-process was dependent on its natural language text or structural text like code, and after that we do the training and evaluate it with the AI metrics, and also some of the partners evaluate in the real world with the real world data. So, and after that we package all of this process. So for example, now here I'm telling about the service classification. About service classification, Sorry, okay. Here, service classification has the same things, but we want to mention service classification data. Here we can, in the left place, we can see the benchmark data set, and it's very imbalanced data, but with gathering data, we find the good balance. We provide a good balance for our training model to have a better result. And after that, here is the service classification model, the result, and based on the model metrics and based on the expert validation, it has a good result and almost satisfying the result. So if I want to say all of the provided model can categorize to the prediction and recommendation and AutoML. Service classification is kind of the prediction, and code, for example, code generation or BPM and suggestion is kind of recommendation. And the last part is the AutoML. We provide, as you can see here, all of the models are packaged and the result, and all of them are serve as API. You can see here the example of the input and output. And the last part is AutoML APIs for the DLE. The thing is, nowadays, most of the software need something like analyze the data, their data, providing some plots based on historical data. So we provide some AutoML APIs that users can use these provided APIs to analyze their data. So sorry for the, and thank you for all. That's it from my side. Thank you.
Thank you, Zaki. Sebastian, would you like to add more, or I have a couple of questions, and I also invite others. If you have questions, please raise them now. Okay, can I? All right, then I'll go ahead with my question, Sebastian. Like I said, I asked earlier that, it's raised by my colleagues who unfortunately could not participate today in the event. So, but, the first question I would like to ask to you, and this is also, I will ask later to the project physics also. So first of all, the current wave, of the proposal calls of the Horizon Europe calls in the cloud computing area includes cognitive cloud, that is using AI to improve cloud computing infrastructure, and swarm computing, programming decentralized and systems with many heterogeneous nodes and devices. So what contributions and lessons learned would you like to pass on to projects that will be funded in these new calls? How can they leverage and build on your experience? That's the first questions. And if you have any insights, that would be great. Sorry, I asked you to unmute. Can you talk now? Yeah?
Yeah.
Perfect, thank you, sorry.
So I think that the first part with this cognitive cloud part, Zaki already explained just in her presentation. I think that's really something what would be very interesting to explore more, and this can, I guess, bring added value. And the second part with the swarm computing, I mean, in SmartCLIDE, we are not so much focused on developing something for the edge, but in the end, whether you develop something for the edge or for the cloud is more or less the same approach. I think what is really something we should all think about is how to reuse code, and not always or most of the times create everything from scratch again. And this, of course, by applying artificial intelligence approaches could support us. Now you are muted.
Sorry, yes. This is a vicious cycle. So the second question that I'd like to ask is, your project includes development tools and environments. Which software developers do you think are the best match for your approach? Programming languages, specific competences, networking knowledge, etc. And where do you think there is a skill gap that should be addressed, possibly at a European level?
So I think developers doing or creating services or cloud-based services, that are the main target group for SmartCLIDE. For programming languages, we try to develop all the things, let's say, technology agnostic, so that we in principle can support any language. And I said in the beginning that we are based on Eclipse-J, so we could in principle support any language that is supported by Eclipse-J, and these are several ones. But our first, let's say, target, or the first experiences we had with Java development. So that would be our first target. And skills gap, I think, yeah, that's a good question. There are several things. I mean, we can go from certification. So do we have certification for developers? Do we have certification for software components? There's a mismatch. Then also that often developers have to do everything from design to test, and then also the deployment. So I think this has to be separated a little bit more.
Thank you. Yes, this skills gap topic is also very close to our project Hub for Cloud. It's one of the core topics that we are trying to map the skills gap, cloud computing skills gap in Europe, and give what is the demand side and what is offered in the market. So we are launching a webinar series, and I'd like to take this opportunity to also talk about this. Probably most of you all here already know that next week on 8th we have the first webinar on this cloud computing skills gap. So if anybody's interested, I'll put the link here in the chat so you can give it a look, and then it's on 8th of March, 1 hour. So if it's interesting, please join. One more question, Sebastian. It just came up from internally that for SmartCLIDE, how do you use or adapt BPMN for intelligent service composition? How flexible can the composition be, especially in dynamic scenarios? Example, edge computing with nodes appearing and disappearing. If this is applicable, or if you can answer, that would be great.
I think this question I would like to pass to Theodoros.
1 second, let me try to unmute Theodoros.
Theodoros, are you there?
No.
Yeah.
Hello, can you hear me? Yes.
Yes.
Yeah. Okay, great. Yes, BPMN is quite dynamic, and you can add and remove nodes on the fly, of course, and the workbench supports this functionality by being very, very easy to build and compile and deploy new workflows that also contain a lot of business logic. Also, it depends on the. I don't know if you mean about the services part, the deployment about Kubernetes or something. If your question had something related to that. No.
I can repeat my question.
Yeah.
If you'd like.
Yeah,
How
sure.
do you use or adapt BPMN for intelligent service composition? How flexible can the composition be, especially in dynamic scenarios? Example, edge computing with nodes appearing and disappearing.
Okay. Okay, now I think I understand the question better, but in order to modify and include more nodes in the BPMN, we would have to change the whole workflow from the start and redeploy it in the cloud. So it's not dynamic in that sense, but the process is very straightforward to do. It doesn't require much configuration, and also we can, for example, deploy a new instance of the workflow while keeping the old ones online, up and running. So, yeah.
Thank you, Theodoros. Thank you, Sebastian, for the presentations from SmartCLIDE. And I'd quickly like to go to the next part of the workshop. We are already 10 minutes ahead. And I welcome now Ariana from the project Physics. Ariana, can you unmute yourself?
Yes.
Yes.
No?
Yes.
Can you hear me?
Yes, perfectly.
Thank you very much. So let me also try to share my slides.
Ariana, meanwhile, when you're sharing the slides, I just wanted to say that if your presentation and also from Georgios can, we try to finish it in the next 45 minutes, so then we, finish on time.
Yes.
Thank you so much.
Right, so can you confirm that you can see my slides now?
Yes.
Perfect, thank you. So I'll try to be quick and then I'll give the floor to the rest of my colleagues. So hello everyone, I'm Dr. Ariana Poliviou from Innovact Limited in Cyprus. My presentation is going to be about the physics project, more or less our motivation, goals, and what we're trying to implement. And then I'll give the floor to my colleague, George Kousiouris from Harkopio University of Athens, who will dive you into our FaaS approach and then the design environment for it. So first of all, let me explain what let me give you the long title of our project, which stands for Optimize Hybrid Space-Time Service Continuum in FaaS. And what is this about? Basically, drawing on cloud computing challenges such as the variability and heterogeneity of service offering, the complexity of underlying programming languages, the volatility of services performance, and also the unawareness of physical infrastructure characteristics and application instructional characteristics. All of these have motivated us to come up with our project vision. Also, let me note here that serverless are the area of public cloud computing services with the highest growth. So basically, the vision of our project is to develop a platform offering from a graphical view in order to allow the drag and drop of commands and create the pipeline of functions. And basically, the project will offer a global computing layer which will deploy function in optimal ways and organize multiple application objectives at the same time. So basically, we want to unlock the potential of the functional service paradigm, one, for application developers, and second, for cloud service providers. So our project goal or goals is to deliver a complete vertical solution which will enable cloud service providers to offer advanced cloud application design environment to create workflows of applications relying on visual flow programming tools, and also to offer platform-level functionalities which can be integrated by the providers and translated into workflows into the FaaS-specific actionable sequences, and also provider local resource management mechanisms, which will enable them to reach more competitive, optimized services through real-time reaction of system failures. Very briefly, physics project is part of Horizon 2020 ICT4 call, which is on cloud computing towards a smart cloud computing continuum. Our project budget is around 5 million, and we have a time frame of 3 years to complete our goals. The project comprises of 14 different partners, and GFT is leading our project. Here is a list of our project team, including partners from 9 different countries, coming from universities, research centers, industry, and several different case studies, use cases that I'm going to present later on, which will serve as pilot sites. And regarding our plan or timeline, in the first phase, which is already completed, we came up with a design. So we did a market gap analysis, we did the requirement solicitation, and we came up with the architecture and the use case scenarios. Now we are in phase 2. So the first phase of our implementation, where we cover the core features and we started the development, and also we do an internal use case validation at this phase. Then we'll move on to extract some feedback from external audiences based on what we have implemented in phase 2. Then we'll go back to implementation again to do the fine tunings and conduct the final implementation. And then we'll have a short phase to conduct validation and assess the impact of our outcomes. As I said earlier, we have use cases in this project. So we have 3 distinct use cases. One that I have here is on manufacturing, smart manufacturing. So our aim is to demonstrate how the FaaS model can be used in the manufacturing and production area in order to optimize production lines. The second use case is in the healthcare sector, in particular in e-health. So how we can provide and support personalized monitoring and collective data analysis. So we'll demonstrate how the deployment of FaaS across multiple Internet of Service devices can serve as a real-world data and help biomaker of diseases extract information. And third use case is on agriculture, in particular on smart precision agriculture. In particular, we want to demonstrate in this case how FaaS paradigm can facilitate the implementation of thousands of daily climatic simulations and can contribute towards improving crop management and yield estimation. This is more or less at a glance what the physics project is about. Of course, if you want to find out more about the physics, you can visit our website, and please also follow our social media accounts for upcoming activities and more information on the results of our project. Thank you for your attention. And now let me give the floor to my colleague, Georgios, who will be able to follow up with the FaaS approach of the project.
Thank you, Ariana. So let me share my screen. Let me see it.
Yes.
Okay. So, hello, we'll be presenting the design environment for function as a service applications in the context of the physics project. This is the main entry point for the developers in the project. And let's start by the motivation, starting from understanding the developers that in many cases, let's say, go through let's say an endless nightmare. So we started initially with the cloud era, with new concepts like ephemeral and scalable resources, the need to distribute more applications. They had to change their applications from the monolithic desktop ones or very centralized ones. Then we went to the microservice era, where they needed to break down the components into more modular, scalable, manageable approaches. Again, they needed adaptation processes. Then we reach the serverless era, in which, again, we need to adapt the application, scalability, an indirect obligation to follow a CLIDE native design, and the need to have applications broken down into functions and executed on demand. So what we have is a continuous process every 4 or 6 years that the developers need to adapt and readapt over and over again. To have a small introduction about what is function as a service, you have here a basic architecture from OpenWhisk, the main FaaS platform we are working with. So one needs to split the application logic into smaller chunks. These chunks are wrapped around functions. This function execution should be stateless in principle. This execution is performed inside the container, launched on demand when a request comes. This request can be external events, other functions calling them, cron jobs, and so on. So you typically have the request coming from Nginx to a controller to a queue, and then to an invoker that regulates, let's say, the invocation to a Docker engine or a backend container cluster in order to execute the function that you have wrapped around a specific container. Aspects here may also include the ability to include arbitrary or legacy application components as a container and execute and just change the execution model. And the costs are based primarily on how many times you invoke a function, how much execution time does a function take, and what is the memory used by that function or by the container that includes the function. So in overall, it's a rather flexible and cost-effective model in most cases. However, it comes at the expense of needing to adapt further the application. Challenges that have been identified either by us or by external research groups. So one aspect is how can these functions become manageable, shared at the group, and reused. There was a mention of reuse in the previous presentations. Imagine now having a very large application that splits down into 100, 200, 300 functions. How is one able to manage that? How is one able to group them, potentially functionality that is reused is somehow aggregated? How is increased complexity expressed in the application structure and logic? How can we aid other aspects such as the design of the application and the testing and the debugging and the deployment process? In general, it is quite time consuming to test a function that then you need to deploy it and on the environment of FaaS platform. So how can we enhance that with potentially moving some of the testing into local environments? How can we automate DevOps processes so that the according deployable artifacts are generated without the significant involvement of the developer? And how we can abstract the overall application design and porting to the serverless paradigm, including the ability to bring in legacy part as much as possible in order not to, let's say, raise too much the cost of the migration process. And finally, how can we link between the design time, the application, the developer needs and goals, the business needs and goals, and how to dictate the deployment and runtime needs? Because serverless and function as a service in general is very nice and abstract, but this abstraction comes at the cost of not being able to be as specific as possible if you want to dictate specific aspects of where to deploy, of priority, or any other such features that you might have in mind. The goal of the physics design environment is, as I mentioned, the entry point of the process. Our goal is to be as versatile and abstract as possible. So in a nutshell, it is to provide some ready-made functionality in the form of patterns, in a drag and drop manner, in a visual workflow programming style, to deploy, at least for the majority of the things one needs to test. And afterwards, to translate whatever you have created as an application to a proper platform specification that is then forwarded to the platform services, that then forwarded to the infrastructure services based on the project stack in order to be deployed and executed on the actual infrastructure. So in that part, we also have a number of semantics involved, the patterns I mentioned in terms of reusable functionalities, and some other functionalities like controllers and extra components that can be used by the application. Also, we try to focus to give many options to the developers in terms of how they want to execute a specific code segment that they have created, on if they want to build a workflow around that function, if they just want to deploy it as a service or include a service together with functions. All of these aspects will be supported in the end. And the ability to include diverse annotations as guidelines that are forwarded from the developer to the management approaches that exist down the stack. In terms of the main technologies we are based upon, initially we have selected Node-RED. Node-RED is a very popular tool, but it was limited to the IoT domain. So typically one can use Node-RED in order to build the smart home automation system, create some simple flows, deploy them, and automate some things. However, if one takes a close look on this, let's say, environment, we can see that it is very closely related to functions as a service in general. So it is based on functions, it is asynchronous, so it fits directly with the concepts included in the domain. It has a large palette of either built-in or community contributed nodes with a very large variety of operations coming from the IoT world, like adaptation to protocol inputs, a way to collect data, transform between different formats and specifications, clients for practically any external system. And it's very easy. One feature that we like a lot, very easy to create, to group functions together, create subflows, and then reassign these subflows, let's say, as new functionality. So you drag and drop in the workflow, you link them together, you may put arbitrary code segments at some individual points, and you create the flow that is then deployed on an operating server that gets executed and waits for events to trigger the flows. Based on the reviewed related work and available platforms, what we also liked a lot was the fact that in an environment like Node-RED, you basically have a unique, or if not a very rare combination to be able to have both orchestration of the workflow, the functions that are included, but also the ability to execute functions directly inside the runtime. And this gives a lot of opportunities about how one wants to mix and match, let's say, different execution modes in the way they deploy or operate an application. So the question was, why not use it, provided, of course, that you undertake the effort in order to create a set of backend services and functionalities that are needed in order to move from this server-based execution to a function-based one. So in a nutshell, the physics design environment consists from a local version that the developer may download in the form of a number of containers, enriched with our contribution in terms of provided nodes and so on. And it has also a set of backend platform elements that are necessary for flow processing, repository management, and so on. Embedded in this process is a DevOps pipeline, let's say, that starts from the flows in the environment once someone creates and designs their flow, tests them within the node. What is done is that a relevant backend component is activated, the relevant flows are retrieved, all the new dependencies and modules and extra libraries that are included in the environment are, let's say, used in order to build through a Jenkins pipeline the final deployable code artifact. And this can be either, let's say, the function code in the form of a zip file as needed by native runtime supported by typical FaaS platforms, or they can be a whole Node-RED environment. So we have three ways of using whatever we design Node-RED. One is to use it primarily as a function editor and deployer. So one can drag and drop pure JavaScript functions or other languages functions in the environment. They can put their own code inside these functions. And then when we obtain that flow, we convert it to the a typical OpenWhisk sequence. And we extract the code, all the dependencies, and we create the deployable function for the OpenWhisk platform. Now, this is, let's say, the main functionality, but this is a, let's say, a basic one, because OpenWhisk by itself cannot support anything more complex than a simple sequence in terms of workflow primitives. So it's not that powerful. And you can also not exploit all the available built-in nodes that are in the Node-RED environment packaged as Node-RED nodes and not pure JavaScript ones. So the main way, as we foresee to its usage in the project, is to have it as a function execution or orchestration runtime of the Node-RED environment. Then you can do a bit of local testing. You can use any node and logic that is available as a built-in node or an externally brought in node. Then the environment kicks in and creates a customized Docker image with the specific flow, including all the dependencies. And it adds that specific Docker image in the supported OpenWhisk runtimes and registers it, given the fact that OpenWhisk, as well as many other serverless platforms, has the ability, as long as you abide by a specific interface, to register any image to be executed as a function. And in the end, whenever the function is invoked, then the overall action image is launched, and the function and the flow you have is executed inside that container. This, of course, has another, let's say, trade-off. First of all, that the image is larger than a typical Node.js image, for example, but it also doesn't have a lot of parallelization abilities, given that all the functions are executed inside the same container. So a variation of this way of execution is to enable the use of Node-RED as an application level orchestrator. This can be run primarily, we foresee most of being the orchestrator function, the most valuable one. And inside that, you can orchestrate actions that are functions. Actions are the function name in OpenWhisk terminology. So you can orchestrate the execution of existing actions in OpenWhisk through a Node-RED flow that you have created. And the third way is if you use it as a generic wrapper around legacy logic. So I imagine that you have your own image. You don't want to spend a lot of time in order to migrate to the FaaS model, but you want to exploit the benefits of this execution. So what you can do is you can take your baseline image, enhance it with the Node-RED environment, and then create an adaptation flow on top of that. We provide patterns that have to do with the defined interface of OpenWhisk, then some example adaptation processes that is very easy to do due to the various functionalities that are inside Node-RED about message manipulation, format transformation, and so on. And then you can basically launch your main execution script without a lot of adaptation. In terms of semantics, as we mentioned, this is one of the elements of the environment. What we wanted to support is the ability to provide annotations, both at the function level and at the flow level. So for that, we have created two ways of providing these annotations, either with custom nodes that we create and they are registered as Node-RED nodes, or through a code level specification for annotations at the function level and the code that you write. So then once someone creates, let's say, the flow and then wants to proceed with the steps in the platform, intermediate is that they extract the annotations that are included either in the nodes or inside the code, and map them to a relevant ontology that we have created in the context of physics. I have put in the link if you want to see the current version. And this transforms basically the Node-RED specification of the workflow, JSON specification, and enhances it with JSON-LD descriptions that map the specific, let's say, concepts of the used by the developer. They map them to the format. And then the semantics are stored and propagated to the underlying management layers. So the ways of annotation in a nutshell, as I mentioned, through code level annotations, if you can see the image here, so it has a specific notation for using it, or with specific nodes that have elements that have to do with some form of configuration that you want to apply. Example of annotations that we have initially included is whether you want to dictate some relative placement. So within a cluster that you have, if you want to define affinity or anti-affinity between flows or between functions. If you want some form of absolute placement, so if you have a set of available nodes, clusters at the edge of the cloud, or so on, if you want to specify for specific flows that they need to be at the edge, for example, or at the cloud. If you want to replicate that location, that function in different locations, because you might have these different clusters, and you want both cloud and edge execution, function registration to both these environments. We have also other layers down the infrastructure stack that have to do with scheduling considerations. So we support in the end a number of different scheduling decisions in terms of energy-aware schedulers or performance-aware schedulers. You will be able to annotate what is your optimization goal for a specific function or a flow. If that flow or function is important, meaning that it can get priority on its execution or on the number of reborn containers against other functions and so on. And then some other more typical ones like sizing or QoS constraints, the memory of the container you want the function to be executed in, and so on. And the last part I would like to cover, so that we have time, so is about the patterns. So as mentioned, one of the major goals is to group functionality around a specific issue. So the idea is to be able to give out patterns to developers that are ready-made flows. They can be used in a similar problem, potentially with a specific objective, initial conditions, and a certain context to apply them, and by the offering through the Node-RED palette. So as an example, one of the first patterns we have implemented is a fork join parallelization pattern. So in that case, you have a ready-made node in the Node-RED palette. You can bring it in your flow, and what this node, this subflow does, you can see here the implementation, is that you can feed it with an array of inputs. These inputs are split then into individual messages, and these messages are forwarded to the, let's say, execution element. And the execution element, in that case, is a client of OpenWhisk, for example, that triggers the execution of parallel functions that cover parts of the input. And in the end, they wait for all the executions to finish, join the results, and you progress with the rest of the logic. Also, we have added variations here in terms of where the actual execution will take place. So the typical case, as we expect, it is through spawning multiple OpenWhisk actions against the cluster. We have also variations that include the execution through local processes if you have these let's say legacy scripts that you want to execute. One aspect here that also we need to further automate in the future and support through more intelligent means is how you split the size of the array input, because obviously if you have 1 million rows and you put them like that in the pattern, you will end up with 1 million containers. So this would create a lot of interference overheads and so on. So one extension here for the future is how to dynamically control, let's say, the split size in order to, or to optimally set the split size based on your cluster size so that you can indirectly dictate how many containers will be spawned in the end. Also, we have another set of patterns, an issue that is very tricky in the case of function as a service. In function as a service, there is especially for OpenWhisk, there is the concept of hot containers, meaning that once you have a, let's say, a function invocation, the container is launched, it executes the function. Any context that has been created during the first invocation remains in the container. The container itself is paused for some time so that a new function, if a new function invocation comes for the same function, then it reuses the same container. If it doesn't, then the container is deleted after 10 minutes, 12 minutes, and so on. Now, what is tricky in this case is that the second invocation will start by having the context of the first invocation already in the container. So basically, this creates both a risk and an opportunity. Okay, a risk because obviously you may not want context from previous executions because they might belong, for example, to different users, or because they might mix up with some functional aspects of your logic. However, what you gain is the fact that if you have, let's say, if you need, for example, a token to access an external service and you have retrieved it in the first execution, you don't need to retrieve it again. So in general, this feature can be both hazardous, this, let's say, approach of FaaS is both hazardous from security or whatever functional point of view, but it can also be beneficial from a performance point of view. So in terms of context management they need, we have formulated context management under 3 different patterns. So the default behavior is the typical one of FaaS. So we named it as opportunistic context reuse, opportunistic in the sense that sometimes you might find it if the invocation comes within the post time. Sometimes you won't if you invoke the function after the post time. And it's the default behavior that we have through the environment. However, we have two other options as well. So the tabula rasa skeleton pattern. In that case, what is done by the pattern itself, the provided interface that we give, is the fact that we clean up any context between different executions. So the flow itself can be executed without any context reuse aspects because it's cleaned by the pattern itself in the beginning. And the second and the third option that is currently work in process is support a pattern in the end that will be able to maintain the context in an external service. So whenever the function is executed, the first step is to retrieve any context from an external store, run the flow as usual, and then any newly created context is restored in the final in the external store as well. So it's all based on the developer options. Physics has gone, let's say, has put a lot of effort into giving out different options to developers, the issue, and so on. This is an example of the tabula rasa pattern that let's say includes the extra steps in order to delete all context from the environment. Other types of patterns that we have, specifically for edge cases, we have an edge ETL process. So this is to enhance the reliability aspects of data collection at the edge. We have such specific use cases, the smart agriculture use case that Ariana mentioned. The use case reports a lot of reliability issues when collecting the data. They report also a lot of trouble when they want to adapt to different greenhouses because they go and put their solution. They need to collect the data from the greenhouses, and these greenhouses typically may have different implementations, different protocols, many different things. So in that case, what we exploit is the diversity of node-RED in the IoT domain. So it's much easier to do an ETL process and collect the initial data through node-RED, through all the protocol nodes and transformation that it has. Let's say local storing processes, trying to push the data to a cloud service. Networking is another, let's say, bad aspect at the edge in that specific use case. So to handle aspects such as trying to push the data, if that doesn't succeed, you store it locally, and then at some point in the future, you are able to retry pushing the data. And this is very critical for a number of use cases because when they go a long way to simulating, for example, how a plant grows, and in the end, you end up with 40 or 50% missing values in a day. So then they need to estimate these values, and by including the estimations, the final, let's say, error of the simulation gets significantly increased. Also, we have other patterns in order to assist in the creation of a workflow in the form of workflow primitives, being able to join, for example, messages in a correct manner coming from branches that may have different timing, let's say, characteristics, slower or faster branches. And request aggregations in the form of that if you want, for example, to minimize the stress you have on your backend or minimize the number of function invocations that you have. You have a kind of preprocessing layer acting as a service where you gather requests, and there is a controlling logic through which the requests are merged, and then they are forwarded as a batch to be accommodated by the backend. And a number of other helper let's say functionalities like asynchronous read writes and so on. That's it from my side. Thanks for your attention. If you want, you can give a small demo also of the question.
Thank you, George. Are there any questions from the audience? You can write in the chat, or if not, then I have the couple of questions that were passed over to me from my coordinator of this project of Hub for Cloud. So I'd like to raise them. George, if you can answer, that would be great. So there is this first question: the current wave, the deadline in a month from now of the Horizon Europe calls in the cloud computing area includes cognitive cloud, using AI to improve cloud computing infrastructure, and swarm computing, which is programming decentralized in systems with many heterogeneous nodes and devices. What contributions and lessons learned would you like to pass on to the projects that will be funded in these new calls? How can they leverage and build on your experience?
Well, I can give you, I had time to think about the answer. You mentioned that in the previous session. I think what is had a lot of thoughts and considerations was during the selection of the baseline toolkits. So what it seems is that so when we wanted to select which kind of FaaS baseline platform we are going to use, we saw a number of very nice solutions. We saw Kubeflow, we saw OpenFaaS, we saw Knative. And these are let's say the very prominent ones. There are also other 3 or 4 ones. Now, what was evident was that in many cases, a number of different toolkits exist. None of them is perfect, obviously. They are all typically tailored for a specific domain, a specific use case. We liked very much features of one aspect, the features of another. We ended up with a selection that covered the majority of cases, but we wouldn't like to be stuck with that solution. So I would say that because there is a sense of continuum in all these project EEC project calls, I would like to say that one particular aspect is about having a service continuum. So how can we write an application that could be migrated to different stacks? If we write an application, for example, that we write it in Node-RED, how easy it is for us to go then not to OpenWhisk, but to another solution? Why do we have to marry the whole stack below? That would be some very interesting aspect from my point of view. The ability to move from one stack to the next in a minimal, that would be a great, let's say, focus.
Thank you. Can I move on to the next questions that I have? Very quickly, just a brief answer would be great. Your project includes development tools and environments. Which software developers do you think are the best match for your approach? programming languages, specific competences, networking knowledge, etc.? And where do you think there is a skill gap that should be addressed, possibly at a European level?
Yeah, I think that different types of developers. So they have, let's say, scientific developers doing simulations, developers coming from the scientific community. They are typically, not that of a developer. They're more, other types of scientists. They have development knowledge, not that large. We have data scientists in the e-health use case. So we have, let's say, we have a variety of people that are not they are not in principle, they can be not in principle, not the core developers. So I think that in our specific case, the goal was to give to such intermediate, let's say, developers the ability to adapt their existing processes in the environment. And through the use of the patterns, they may have functionalities that they are abstract from them, and they don't necessarily go into a large detail about how to use them. Ideally, developers that are more in Node.js or Python, these are developers that are probably more affected by our solution. But as I mentioned, because we have this porting of the existing legacy code, other types of developers can be used. So for the other question was about the gap you mentioned, the knowledge gap. I think in general, there is a gap into more organized DevOps processes be fully exploited. That's something that potentially could be enhanced. And I would agree with the speaker from the previous session about the reuse of the code. So not try to do the same things over and over again. Mm-hmm.
Thank you. One very last question, but if you can answer it very shortly, can you give some example of the ontology you mentioned? I think it was slide 12. How is it used and what kind of artificial intelligence techniques are or will be adopted?
At the moment, so I assume you mean about the concepts that are included in the ontology.
Sorry.
So you mean about the types of relationships and concepts in the ontology?
Yes. Can you give some examples of the ontology mentioned in the slide 12?
Yes, I think there's a link. We have an online version, so you can also see it, see the relationship directly. The main, first of all, describe the application. So when we say application in the context of physics, we mean potentially a collection of flows. So in this, when we create the triples in the end, the description, this might include the different flows, the JSON specification as it is extracted from Node-RED, all the annotations that the user has added. So a flow has an affinity consideration to be scheduled together with the other flow. So, or an anti-affinity consideration. We also group let's say, try to model the structure of the function so that function A is linked to function B and then linked to function C and so on. So we map that structure as well. We map all the functional aspects so that we also have all the information in one place so that this function has it. This is another example of a triple we extract in the end. so that then when this information comes to the underlying platform layers, it has all the information needed for the deployment and for the management in that description. Other concepts that we have included or we want to include in the future, that's potentially the focus of an AI processing afterwards, is whether the patterns, typically the patterns are created for a specific goal. And you should not be using them if you don't have that goal, because they typically enhance that goal while deteriorating something else. So the idea would be then to create such links between patterns and the usage of the function. So to determine whether a pattern would be beneficial for that function or for that workflow. Other aspects would be how patterns can be conflicting with each other. So this could be either modeled by an expert or they could be reasoned by an AI component together. So patterns and anti-patterns. These are some examples of the structures we have. All the annotations that I showed are eventually placed in the ontology. We also want to automate configuration at some point. So we want to model, for example, control points of the application and include that in the description so that then you can have generic controllers that can regulate parameters of the application. And what parameter do you regulate? The one that is expressed in the ontology. You don't have to know what parameter this is, you infer it from the ontology. So you can have generic controllers that toggle an application parameter that does something, launches more threads or less threads based on the runtime operations that you have. You are muted.
Yes, sorry, thank you. Thank you for reminding. Thank you so much, George. And thank you for explaining it so nicely. Thank you. And sorry that I had to rush you in your presentation, but I hope that you could cover everything, not missing any important parts.
No,
thank you, everybody. If anybody has any questions, more information, inputs, anything, now is the time to say. Just, raise your hand. I'll open up the mic, open up your mic. Otherwise, we say goodbye and we come back again next time with, next month or then the next couple of months, May and, April and May, we have a lot of events coming up. So we see you soon. So I take this opportunity to say bye-bye.
Thank you.
Thank
Bye-bye.
you. Thanks, everybody. Bye.